So we have looked at three basic methods, the Jacobi method and Gauss-Seidel method and the SR method as basic iterative classical iterative schemes. We know how to use these methods to get a solution, but we still have not answered the two questions which are also important to the choice of whether or not to use these things. That is, what are the conditions under which these methods converge, and secondly, what is the rate of convergence. And for this we can formulate a general criterion for the assurance of convergence, okay, but the actual implementation of that will be non-trivial. So let us look therefore at the convergence analysis of the classical iterative schemes. So our classical iterative scheme, an iterative scheme is of this particular type. So we can write phi k plus 1 equal to m inverse n phi k plus m inverse 1 b. Although as we have seen here, we never compute the m inverse and then do this. In the actual implementation it is different from what we have written, but it is good to put this up and in this particular form as the structure of the iterative scheme. As already mentioned, this is the iteration matrix that determines the rate of not only the rate of convergence but also whether or not it would converge. So this iteration matrix here is the key to the behavior of this iterative scheme with a specified decomposition of A into m and n. Okay. So now let us say that the error at the kth iteration is phi k, which is the current estimate of the value phi here, minus phi tilde, okay, where tilde is the exact solution. We can put it as the exact solution minus the approximation that we have. If we have n number of equations, there are n estimations. So we can say that for the ith variable at the kth iteration, the error is the exact value of phi I, which we are denoting by phi tilde, minus the current estimate of that particular variable at the kth iteration. So this is the error here, and so we can we know that the exact solution satisfies this thing. So we can say that phi here is equal to p phi tilde plus q. For example, if we use a direct method with infinite accuracy, we can get this corresponding to that a phi equal to b. But at this stage we are not saying what this value is. Okay, we are saying that there is an exact solution to the a phi equal to b, and that exact solution is given by this. Since a phi equal to b is equivalent to this for a convergent scheme, then the final solution that we get is doing this. And if we subtract this from this equation, we get phi tilde minus phi k plus 1 equal to p times phi tilde minus phi k plus 1. Q and Q will cancel out, and this is nothing but the error at k plus 1, error at k, this is error at k plus 1, and this is error at k. So we can say that from this. We have written it like this to show that the error at k plus 1 at k is multiplied by the iteration matrix P, and this to give you the error at k plus 1. So, this is error at k plus 1 is P times the error at k. Okay, this is a matrix equation. It is not as simple as that, but with any matrix we can identify a magnitude, and that for a matrix is given in terms of various norms of the matrix, and the norm is an indication of that magnitude of the matrix. So, therefore, we say that for error not to increase from k to k plus 1 to k plus 2 k plus 3 like that, or for error to decrease with increasing number of iterations with successive approximations, the magnitude of P or the norm of P must be less than 1. Okay, so, this is the condition for convergence of an iterative scheme. If this is a iterative scheme and P is the iteration matrix, the condition for convergence is that the norm of this iteration matrix must be less than 1. So, that if let us say it is 0.9, if your initial error is 100, then at the first step it is going to be 0.9 times 100, next time it is going to be 0.9 times 0.9 times 100 like that. So, if your initial error is E naught, then according to this E1, and let us put this norm as some small p. So, then this will be equal to P times E naught, and E2 is P times E1. So, that is P square times E0, and E3 is P times E2. So, that is P cube times E naught, and so on. So, that we can say that the error at the kth iteration is Pk times E naught, the initial error. So, the initial error is P raised to power k times this, and for this to be decreasing, P must be less than 1, otherwise this will keep on increasing. If P is 1.01, then the error will increase with the k, and if P is 0.99, then error will decrease. So, depending on whether how close P is, we have P is to 1, we have either convergence or divergence of this particular iterative scheme. And also if P is very close to 1, then the rate of divergence or convergence is also going to change. Okay, so, the effectively what we can say is the rate of convergence for convergence the norm of P must be less than 1, and we can say for these type of equations, when we are looking at constant real coefficients and so on, we can say we can express the same thing here as the spectral radius rho of P must be less than 1, and rho here is the spectral radius, and the spectrum that we are looking at is the spectrum of the eigenvalues of the matrix of the iteration matrix rho, and spectral radius is the value of is the magnitude of the largest eigenvalue of the iteration matrix. So, the necessary condition for the iterative scheme to converge is that the largest eigenvalue of the iteration matrix must be less than 1. So, if you say that lambda is the eigenvalue and lambda m is the maximum eigenvalue, then lambda m must be less than 1. for convergence. So once we construct M and N and once we construct P, the iteration matrix, even before we go through the iteration procedure, we can find out, we can predict whether or not the scheme would converge by finding out the eigenvalues of this thing. Okay. Typically eigenvalues are very difficult to find, especially for large matrices. We can see that in a typical CFD problem with say 1000 grid points or 10,000 grid points, the matrix A will be large. If you have 10,000 grid points, then you have 10,000 eigenvalues and you have to choose the largest of these things, and that largest of these must be less than 1, and it depends very crucially on whether it is less than 1 and how close it is to 1. If the largest value is 1.0005, it is going to diverge. If it is 0.99995, it is going to converge. So we have to determine the largest eigenvalue to that much accuracy. So for large values, the determination of the eigenvalue itself may be very time consuming and it may take n cube number of operations. Okay, so in such a case, although we have a theoretical confirmation here of the necessary condition, this method is not very practical. We have a less restrictive condition which is known as the weak form of the diagonal dominance. As a sufficient condition for the convergence of the Jacobi method, Gauss-Seidel method and SOR method for omega between 0 and 2. So a more readily implementable criterion, sufficient condition, is the weak form of diagonal dominance. And what is this? This is the weak form of diagonal dominance of matrix A, not matrix P, because P is the iteration matrix and that varies for the Jacobi method and Gauss-Seidel method and SOR method. Okay, but for all these methods, your A phi equal to B or the coefficient matrix A is the same, and if the coefficient matrix A exhibits the property, has the property of the weak form of the diagonal dominance, then we can be assured that any of these methods will work. Okay, and what do we mean by the weak form of diagonal dominance? We have the coefficients, so A has the coefficients Aij, and if the magnitude of the diagonal element is greater than the sum of the magnitudes of all the off diagonal elements in a particular row for all rows. Okay, so we are taking row by row. In each row, if the diagonal element has a magnitude which is greater than the magnitude, sum of the magnitudes of all the off diagonal terms, then we have a strong form of diagonal dominance. The weak form of diagonal dominance is that Aii, that is the magnitude of the diagonal element, must be greater than equal to the sum of the magnitude of all the off diagonal elements is greater than or equal to for all rows, and at least for one row it must be greater than at least for one. So if you have m number of rows, for each of the m rows this diagonal dominance condition must be satisfied at least with an equal to sign, and at least there should be one row for which this is satisfied with a greater than sign. And we should keep in mind that we are talking about the magnitudes. For example, if you take the third row, then A33 magnitude must be greater than or equal to A31 plus magnitude, that is modulus of A32 plus A34 plus mod of A35 plus so on up to A3n. So this is the condition for the third row. If this is satisfied for all the rows with a greater than sign, then we have strong form of diagonal dominance. If it is satisfied with an equal to sign for all of them, and at least for one of these rows it is satisfied with a greater than sign, then we have the weak form of diagonal dominance. And this weak form of diagonal dominance is sufficient to ensure convergence of the Jacobi method and Gauss-Seidel method and SR method applied to A phi equal to B, with the SR parameter being between 0 and 2. This condition here is known as the Scarborough criterion. And this is an easily implementable criterion for ensuring the convergence, because all we have to do is, by the time we come to the solution of A phi equal to B, we already know all the elements of Aij, and we can very quickly check whether we are imposing this, whether we are satisfying this weak form of diagonal dominance. And once we ensure that, then we can make use of Jacobi method or these basic iterative methods. Since we want to, if we want to use this as part of a calculation procedure, at the time of discretization itself, we make sure that the discretized equation which finally results in A phi equal to B is such that this condition is satisfied. And we can say that if you are dealing with a simple diffusion, either one dimensional, two dimensional, three dimensional diffusion with constant diffusivity for a steady state problem, then the Scarborough criterion is satisfied. For all the rows we have this being satisfied with either greater than or equal to. For all the interior points which are away from the boundary, we typically have this being satisfied with an equal to sign, and typically for boundary points we have the this diagonal dominance condition being satisfied with a greater than sign. So this happens for boundary points. Definitely for a Dirichlet boundary condition this is satisfied, and typically for a first order Neumann boundary condition, okay, Neumann boundary condition with first order discretization also we have this form is satisfied, and this is satisfied for all interior points. For all interior points this is satisfied with an equal to sign. So for diffusion problems or for unsteady diffusion problems, we can rest assured that this will be satisfied without a source term. But if we have a source term, then depending on whether or not the source term depends on the value of phi, we can either break this condition, okay, or we can still honor this condition. So that is why in the discretization of the source term we have to be careful. For example, if you have a source term which is okay. So let us consider a diffusion equation with a source term. So we are one dimensional diffusion equation. So we are saying d square phi by dx square equal to source of phi, and if you put this as, let us say, a phi square. So the value of this source depends on a constant a and phi square. So if you write this on a one dimensional grid, this will be phi I minus 1 minus 2 phi I plus phi I plus 1 by delta x square is equal to a phi I square. So this is a non-linear source term. So we can linearize it, for example, in the Picard way. So we can say that this is roughly equal to a phi star and phi I, where a phi, this is some guess value, and we can convert this into an iterative scheme, for example, by making this as k plus 1, k plus 1, k plus 1, this as k plus 1, this as the previous value of k. Okay, so we can do it like this. If we do that, then we can bring this to the left hand side, and we can say that phi I minus 1 k plus 1 minus 2 minus a phi I k. Okay, so because I put this minus, this becomes this phi I k plus 1 times, of course we have delta x square, and we have plus phi I plus 1 k plus 1 equal to 0. So this is the resulting discretized equation, and you can see that this is for the ith term, and this is the coefficient of the diagonal coefficient, and these are the off diagonal coefficients. In the absence of the source term, this 2 here matches with 1 and 1 for all the interior points. At the boundaries, at the left boundary, that is at I equal to 0, then this term will not be there. You will have minus 2 here and 1 here, which is greater than that. So this is satisfying for the left boundary with a greater than sign. The sum of the coefficients without the source term, okay, for the left boundary is minus 2 for the diagonal term and plus 1 for the off diagonal term. Again, at the rightmost boundary, at which point you do not have I plus 1, so you have only I minus 1. Again, it is satisfying that with a greater than sign, but for all the values, for all the interior points between 2 and n minus 1, where n is the last value on the right hand side and I equal to 1 is the first value, you have 1 here, 1 plus 1 is 2, that is the sum of the diagonal off diagonal elements is 2, and the diagonal element itself is 2. So in this case, without the source term, the weak form of diagonal dominance is assured for us. Now the presence of the source term here is adding a times phi k times delta x square to this. Now what will this do to the solution? Is this going to be spoil the diagonal dominance, or is going to help in the diagonal dominance? That particular thing will be determined by a, which may be positive or negative. We have not put any condition on that, and of course the value of phi I k. So let us say that phi I is always positive. Then if a is positive, then the diagonal value is enhanced by adding to this 2. Okay, but if a is negative and phi I is positive, then this will be subtracting it. Let us say that this value is this thing is minus 0.5 and this is 2, so this becomes minus 1.5. So this is the diagonal element value, and the off diagonal is 1 here and 1 here. So the sum of this 1 plus 1 is 2, and the magnitude of the diagonal element is 1.5. So that means that we are not able to satisfy even the weak form of diagonal dominance condition from the source term. If the source term is such that this a phi delta x square is positive, if this is plus, then this becomes 2.5, and this is going to be greater than this. So even for interior points, this will be greater than the sum of the off diagonal elements. So in the case where you have a source term, we have to be careful that the diagonal dominance condition may be violated, okay, depending on what is happening here. If you have no control over phi k, then it is difficult to predict a priori whether it is going to be enhancing it or suppressing it, okay. But if you know that if you have a condition that phi k is always going to be positive, then by knowing whether a is positive or negative, we can see whether the presence of the source term, which is linearized in this particular way, okay, is going to make us lose the diagonal dominance or enhance the diagonal dominance. So we have to be careful in that. If a happens to be negative, then of course this becomes, we are going to lose this. So if a is negative, for example minus phi i k plus 1. So no matter in that particular case, we are always going to lose this, provided delta x square is okay, provided phi I k is positive. So we can in such a case we will not be able to apply the Jacobi method or Gauss-Seidel method or SR method, because there is no guarantee that we are satisfying the Scarborough condition. So in such a case, we have to treat the source term differently. We can't write it like this. So in let us put this as minus phi I square. So in this case, what one could do is that instead of writing it like this, I can write this as minus phi I square, phi I k whole square, where I am using the entirely the previous value. And what does that do to my discretization? Because this is known for the k plus 1th iteration, this remains on the right hand side, and the value on the right hand side, that is the terms in the B matrix, do not have any bearing on the P matrix, and we do not have to worry about whether it is going to, that is, it will not influence the diagonal dominance condition because it remains on the right hand side. But if you express this in terms of k plus 1 and then bring it here, then we have a potential problem in terms of correcting it. Okay, so this type of approach, where some of the terms which influence the value of I at k plus 1 are evaluated with the kth value, the previous iteration value, is known as deferred correction, a correction which is postponed. So this is one way of accounting for a source term which is going to spoil my diagonal dominance. Okay, so with this deferred correction approach, I can treat this using this or even some of the values which may be appearing in this. I may be treating them in a deferred correction approach and push them onto the right hand side of the overall equation, so that my matrix still remains diagonally dominant, at least weak form of diagonal dominance, and therefore I can go ahead and use my Gauss-Seidel method or SR method and work with the solution. But because we are using an approximate value here, the next time round we have to correct this, the next time round we have to correct this. So the overall rate of convergence of this deferred correction approach will be compromised. So, we have to pay the penalty of that decreased rate of convergence of the overall scheme with the deferred correction, and sometimes if the value of this is going to dominate this, then we may not have good convergence at all, we may have divergence. So, the deferred correction approach is a practical way of dealing with terms which are going to spoil the diagonal dominance condition. So, if we have made an a priori decision to solve the matrix equations, that a1u equal to b1 and a2v equal to b2 and a3p prime equal to b3, all those things are matrix equations. So, if you have made an a priori decision to solve those things using Gauss-Seidel method or one of these basic iterative methods, then we have to ensure that in no condition this a1, a2, a3 become they lose the property of diagonal dominance. So, in such a case, for those terms which are going to create us problems, we have to use deferred correction approach, and the deferred correction approach may mean loss of overall convergence. We have to be wary of that, and if we have that, what do we do? In such a case, it means that we cannot use the Gauss-Seidel method, we have to go for a different kind of solver which does not have this diagonal dominance condition. And what kind of solver? We have already seen Gaussian elimination method, LU decomposition method, these do not require Gauss diagonal dominance. So, we can use those things, but they have n cubed number of mathematical operations, whereas the Gauss-Seidel method may have n square number of operations. So, we have to pay the penalty of more number of mathematical operations, more computational time in order to get a solution. So, we have to choose between not getting a solution at all by insisting on a solution method which depends on diagonal dominance, or getting even a late solution using some other method. Okay, we do not have only the Gaussian elimination or LU decomposition for this, we have other methods which do not depend on the diagonal dominance condition. For example, the conjugate gradient, but conjugate gradient method is more complicated to program than Gauss-Seidel method. So, we have to at some point we have to pay the penalty for having a problem which is more complicated than the simple cases that we have to do, and that is where one's ingenuity and one's perseverance in getting a solution, all that comes into picture. So, the point that we want to make here is that the basic iterative methods, the Jacobi method, Gauss-Seidel method and SR method are very simple to work with, but they have a stringent criterion, which is that the Scarborough criterion, which is readily verifiable, has to be satisfied in order to have the assurance of convergence of this, and that Scarborough criterion imposes a restriction on the type of discretization that we have to do. And one example that we have given is a diffusion equation, a steady state diffusion equation with a source term which is of this particular form. When you discretize it in a straightforward manner using the Picard correction to non-linearize this, to linearize that particular term, then we can get into problems with the loss of diagonal dominance. If we do it with a, we can therefore do it with a deferred correction approach and still use the overall Gauss-Seidel scheme for that. We have to pay the penalty of delayed convergence, okay, or we have to go for some other method for the solution of this. We have seen that in this particular case we are going to get a tridiagonal matrix, but in a tridiagonal matrix without the diagonal dominance, the Thomas algorithm may not work. So, we have to be wary of that. So, we have to do things more carefully in cases where we have a source term and there is a possibility of loss of diagonal dominance. So, this is about the condition for convergence of the basic iterative methods. Now, what about the rate of convergence? We have mentioned that the condition for convergence depends on the iteration matrix P, and the largest eigenvalue or the spectral radius of that particular iteration matrix determines it has to be less than 1 in order for it to converge. And when you are dealing with typical cases, then and if you are dealing with a case where you want to have a stringent condition for convergence of the iterative scheme, that is when you want to have an accurate solution for phi, maybe 5th decimal accuracy or 10th decimal accuracy, like that. So when you want to go down to very accurate calculations, then the rate of convergence depends also on the spectral radius. So the spectral radius will not only determine whether or not it is going to converge, but it is also going to determine the asymptotic rate of convergence. Okay, the asymptotic convergence rate is an important quantity when we characterizing the goodness of an iterative scheme. And what we mean by asymptotic convergence rate is the number of iterations that are needed to reduce the error by so much quantity. When we look at any particular solution, we do not know the exact solution a priori. So we do not know what is the error, and so we cannot define exactly by how much the error should be. Okay, but it is possible to get some idea, some assurance that whatever that initial error is, that is going to be reduced by so much factor, and that is based on the eigenvalue of the eigenvalues of the iteration matrix P. And for a given matrix P consisting of n variables, we will have n eigenvalues. So these can be ranged in the order of increasing magnitude of these eigenvalues, and the largest eigenvalue is going to be the one which determines the rate of convergence or the asymptotic rate of convergence. And that we can see because we have said that the error at kth iteration k plus 1 is lambda times k times error lambda times error at the kth iteration. So that is, as we go from kth iteration to k plus 1th iteration, the error is multiplied by lambda. This lambda here, as k tends to large values, this is the value of the largest eigenvalue. Okay. So if the largest eigenvalue has a magnitude which is less than 1, one can see that with each multiplication the error is reducing by a factor of lambda, say let us say 0.9. Then for the next iteration it reduces by another factor of 0.9, so that is 0.81 of the value, and if you continue to sufficiently large number of iterations, then this factor can be the error can be reduced. So we can say that this is equal to, we will just denote this as the spectral radius. So this we can say is rho square k minus 1, that is equal to rho cubed k minus 2, like this up to rho k, the initial error. So the initial error that we had at the beginning is multiplied by rho to the power k. So if you say that the error has to reduce by a factor of 10 minus p, okay, 10 to the exponential. For example, if you say that p is equal to 2, then that means that the error reduces by a factor of by a factor of 10 to the power plus p. So that means that it reduces by a factor of 100. So that means that the initial error divided by error at k number of iterations should be 100. Therefore, the error at k number of iterations is initial error divided by 100. and if you say that p is equal to 4, then error at the number of k prime number of iterations will be the initial error by a factor of 10,000. So we can see that if we define it like this, then we can say that the error at certain number of iterations has to be a factor of 1 by 10 to the power p number of the initial error. So therefore we can say that 10 to the power p is equal to E0 by Ek, and E0 by Ek is equal to 1 by rho k. Okay, so this is equal to rho minus k. So now we can take this relation, therefore we can say that minus k is p ln of 10. Okay. So we can say that k is equal to 2.303 p by ln rho minus ln rho. Okay, so that means that this implies that the number of iterations required to reduce the error by a factor of 10 to the power plus p is given by 2.303 times p, where p is the exponent, divided by minus ln rho, where rho is the spectral radius of the iteration matrix. So when p is equal to 2, then this will be 4.606 divided by minus ln rho, and when p is equal to 4, then k is equal to this, k will be equal to so times this, so this 9.212 by minus ln rho. And what we see from here is that for a given matrix the spectral radius is fixed. Okay. So if you want to go from an error of 100 times to error of 10,000 times, so that is to reduce the error by 2 orders of magnitude, the number of iterations, further iterations is fixed. Okay. So per 1 order of reduction we need 2.3 divided by minus ln rho type of equation, minus ln of rho is the number of iterations. Therefore if you were to say that error reduction factor versus k, where k is the number of iterations, we know that as so this is equal to initial error by error at k, and we know that for a convergent scheme, as k increases, this error reduction factor should increase because the error is decreasing. This is fixed value, so this value is going to increase with k. Okay. And how this increases is eventually in the initial cases the error reduction factor does not depend only on the spectral radius or the largest eigenvalue, but it also depends on all the n-1 eigenvalues which are less than the spectral radius, which are less than the so in that case the reduction, they may not even be reduction, it may be going through like this, but eventually it will go into a constant slope like this, a constant variation, where with increasing number of iterations, then it reaches a constant thing where we are looking at k versus log of p. So, this we take in terms of logarithm value here, then we get a straight line between k and this. So, this slope here is such that when we reduce, let us redraw this. After some initial things, it will be a constant line here. So, this, if let us say that this is 10 square, this is 10 cubed, 10 4 like this. So, this error reduction factor is put on a log scale like this. The number of iterations required to reduce the error from by factor of from this to this is the same as the number of iterations required to reduce this from 10 to the power 3 to 10 to the power 4. So, that means that if you are putting in decimal space, the accuracy of the solution in terms of the decimal place accuracy. So, if you say that the value is 1.00005 is the exact value at the end of 100 iterations. Okay, so, if you say the value is arrived at 0.01234 and let us say that this number is 15. Okay, so, at the end of say 115 iterations you have this value. At the end of 130 iterations, that is another 15 iterations, you get a value which is 1.01. This is now fixed and we will have say 1935 like this. So, and at the end of 145 another 15 iterations, this is accurate only up to this thing. Now, this is accurate up to this, it is only these numbers will change. So, it will be 1.011 8359676 like this, and at the end of 160th iteration this will be 1.0118. Now, only these numbers will further change. So, this is 2 3 4 5 like this, and 175th iteration any further variation will only be in this. So, all these digits are fixed. So, that means that once you reach this kind of stable condition, once the influence of the lesser eigenvalues less than the maximum eigenvalue is taken out, then you reach a stable convergence regime in which the error reduction happens at a constant rate per decimal place accuracy. So, and if we say that we have reached that condition at the end of 115 iterations, then we know that in a computed solution, by the fact that from 115 to 130 as you go with the 116 117 like that, as we see the second decimal place stops changing. Okay, from here onwards it is the third decimal place up to third decimal place it remains the same, it is only the fourth decimal place is changing, and further on it is only the fifth decimal place that is changing and sixth decimal place like that is changing. So, that means that one can loosely say that this solution here is accurate up to second decimal place, and this is accurate up to third decimal place, and this is accurate up to fourth decimal place, this is accurate up to fifth decimal place. So, we want, if we want to increase the accuracy, the decimal accuracy of the solution, we have to have another delta k number of iterations, and that additional number of iterations is given by this. Okay, it is given by 2.303 divided by ln minus ln rho. So, this is the asymptotic convergence rate, and this is determined only by for long values of k. Okay, for large values of k, after we have gone through that initial transient period and after we fall into this asymptotic regime, then further accuracy of the decimal place accuracy of the solution that we get depends only on the maximum eigenvalue of the iteration matrix. So, if the iteration matrix changes, then the asymptotic convergence rate of the method also changes. So, if you take iterative solver like the Jacobi method or the Gauss-Seidel method or the SOR method, in each case the iteration matrix changes, and for different values of the over relaxation parameter in the SOR method, the iteration matrix changes. In such a case, each of them has a characteristic spectral radius. Okay, so that spectral radius will determine how many more number of iterations I need to do with that particular iterative scheme to gain one decimal place accuracy in the solution, but only after we have reached that asymptotic convergence rate. So, this gives us a method of estimating what is the number of mathematical operations that are required to get a reasonably accurate solution using the iterative scheme. We know that we cannot directly compare an iterative scheme with a direct method in terms of the total number of mathematical operations that are required to get a solution. That is because an iterative scheme is only improving the solution and it is asymptotically improving the solution. So, by definition there is no end to the iterative solution, okay, but using this property of the iterative scheme, that after a sufficiently large number of iterations, further accuracy of the solution is determined only by the spectral radius of the iteration matrix. Making use of this, we can get an estimate for what is the number of mathematical operations that are required to achieve a certain decimal place accuracy of the solution, and that will give us an idea of the total number of mathematical operations that are roughly required to get a defined accuracy, and therefore it gives us an estimate of the total number of mathematical operations required for the solution of A phi equal to B. So, that knowledge, that estimation requires a knowledge of the spectral radius, and the spectral radius depends on the iteration matrix.